Any questions? Krishna got a haircut. That's cool. Is it do it yourself?
No, the guy actually lives with me. He cut my hair and he did a very good job. But then I thought that he didn't do enough and tried to do it myself.
I
And
see. Very good. So let's start by looking at the homework 3 solutions just briefly. By the way, for the midterm, it will be problems that were covered until homework 3. So the topic we are going to do today will not be covered on the midterm, but there will be a homework immediately after midterm where you will have to go through this. So don't ignore it just because it's not on the midterm. It will definitely be a big part of the final and things like that, and important for later stuff. But the midterm will include topics till this homework 3, which can lead to a lot of problems. So first problem, most of you got it right, except some of you managed to get twice the answer for the heat capacity. So go through it carefully and see how did that happen. Second problem, almost everyone got right. Some of you missed drawing the curve, which is it asks you to draw a sketch. If you don't draw a sketch, I cannot give you full points, right? I have put it up a few points. The problem that was most interesting, which a lot of you got wrong, is problem 3b. And I'm going to talk about problem 3b in my notes in just a moment. And after that, problem 4, some of you went through very complicated answers, but I have given full points if you just wrote this. The key idea being that phonon is not like having a pencil in my hand or having a glass of water. It's an abstract concept. It's really abstract. You're talking about the quantum number, and these quantum numbers can just change from 0 to 1 to 2 to whatever, depending on energy fluctuations in the system, which is what written over here. That's the whole idea. You can have as many of them. I mean, this is not written in the most eloquent manner, but you get the idea that they just fluctuate because they are abstract quantum numbers. They are quasi particles. They can just fluctuate due to energy fluctuations. The probability of such a fluctuation might be small, but you don't have to. It's not a concrete real particle. But now let's talk about problem 3b. So problem 3b had 4 parts. I think everyone got part 1, 3, and 4 right, and maybe half of you got part 2 right, and half of you did not. In part 2, let's go back to this and look at it. So the problem said that you have classical statistics for indistinguishable particles. So you calculated your classical statistic for distinguishable particles, and you said there are 2 particles, so I'm going to divide by 2 factorial, and I'm done. There is a reason why that is not correct. The reason that is not correct, and after this class, I'm going to send you 2 pages, one from Macquarie's book and one from the States of Matter book by Goodstein, which has a nice page-long discussion on this topic, but I will give you the gist of it. The reason why this dividing by 2, so distinguishable to indistinguishable, can often works by q indistinguishable is equal to q distinguishable divided by n factorial. And it's often. There are many times it does not work. Well, not many. In reality, it actually works more often than you might think. But the reason for this to work is when number of states in the system is much more than number of particles. That's when you can divide by n factorial. So you have so many states and just so few particles that you naturally approach the low density limit. In the low density limit, you will have one particle over here. Maybe let's draw a star to show the particle, a red star. So you have one particle over here, one particle over here, one particle over here. The odds that you end up with 2 of them in the same box are just very, very low, correct? Because you have so many states. And as soon as you have two of them existing in the same state, you cannot do this division by n factorial business. You have to go and calculate it explicitly. And that's the problem here. If you look at part A, you had two particles existing in the same state. That's how you wrote it down, right? So you cannot just divide by n factorial. Now, in reality, this is almost always true, except things like helium at low temperature and stuff like that, where it starts to break down. But that's the main idea here. Be careful, and you should have had a hint, and maybe that's why Meenal asked this when we were doing it last time. The n factorial shows up in special cases, right? In the low density limit. That's where the n factorial showed up by reverse Stirling approximation. So don't feel bad about the 10 points that you lost, but hopefully you will remember for the rest of your academic careers that don't just divide by n factorial without thinking twice. If you are going to have things like this, where more than two particles can exist in some state, then you can't just divide by n factorial, right? So, and think about if those of you who have done permutation combination, things like that, when you're picking balls out of boxes or things like that, the notion of dividing by n factorial happens when you're picking one thing out of one box, right? If you're picking more than three things out of one box, the problem is very complicated then. And that's what happened here. And that's why many of you lost points. Okay, any questions about this?
So in classical physics, isn't like indistinguishable or distinguishable, like doesn't that not make a difference to like the physics of the particles?
It does make a difference, and that's the Gibbs paradox. If you are not dealing with the n factorial carefully, n factorial solves most of the problems. So the reason people introduced n factorial, and this is why I mentioned the Gibbs paradox, and I have not described it in detail because I want to think about it. It will come up in a homework or in a midterm. Watch out. And I will define the problem there. I won't just say, tell me what's Gibbs paradox. I will define the problem. If you don't divide by this n factorial, you can lead to inconsistencies. If you divide by it, these inconsistencies are resolved. It does not mean that is always correct. That's the idea.
Okay,
it is correct in the low density limit.
But even in the non-low density limit, if you have a fixed n, then does it not matter whether they're distinguishable or indistinguishable?
Classical physics assumes, I think we have to look at the problem carefully. If you're thinking about a protein with different residues, right? With different namings of the different each and every residue, then it matters. But if you're looking at a crystal where every atom is similar, then they are not distinguishable, right? So it becomes a bit problem specific, if I understand your question correctly. Does that help? So you have not all classical problems are permutation invariant. Let's put it that way. Okay. Many problems in biology tend to be permutation invariant, depending on many problems in material science tend to be permutation invariant. Many problems in biology tend not to be permutation invariant. For example, like the example I gave of the protein, you cannot just say residue 1 is the same as residue 14. They are really different, right? But
yeah,
that's what I can say.
But like if you had water, each water atom is like diffusing around. So
yeah, that's why I said even in biology there is a differentiation. The protein atoms, look, I did not mention water, right? So you're absolutely correct. The waters maybe you can treat in a permutation invariant way, but not the protein atoms, right? Yeah. So when you write the partition function, you have to be careful. Is it permutation invariant or not? This problem 3, by the way, is a very famous problem on qualifying exams. So those of you who in chemical physics or in physics might see it at some point in your calls, and then you will thank me. Okay, any more questions? Oh, I also wanted to mention problem 1. Problem 1, many of you did a shortcut. You just wrote down equipartition and said, oh, it's done. I deducted a few points because there was a particular way of solving it as it's done in the homework model solution. It's a StatMech class. So I didn't deduct all your points because your answer is correct. But I expected you to use tools that we have developed in the class, which 70% of you did use the tools and you got full points. Some of you did not use it, so you lost a few points. And I think that's fair. Okay, any more questions? All right. So once again, for those, maybe some of you will not watch the video, just look at the notes. So midterm one will include material. Let's make it very specific. Before and on 3/25/21. Okay. Not today's material. It won't be on the midterm. I think 3/25/21 was the last time we had this class. Yeah, so it will include material till there. Okay, great. So let's start. So now we are starting a new part of StatMech, which is, so what did we do? Our first part was just developing the formalism, the ensembles and how to look at things. In our second part, we applied it to non-interacting systems, where was it Meenal or was it Grishma who pointed out last time that it's a bit of cheating when we are talking about fermions to call it non-interacting systems, because the fermions don't go more than one in one quantum state. But apart from that little bit of cheating, they were really non-interacting systems. In our part 3, we are going to look at interacting systems. And as you know, most of life does have interactions between different things. So this is quite realistic. Even though the non-interacting system bit can be quite powerful, as we saw, we were able to get heat capacity versus temperature for electrons and phonons and the black body radiation, all these wonderful things through our non-interacting formalism. But a lot of life is interacting system. And another way of thinking about this is called classical fluid. So we are not going to really think about quantum interactions. We will still be doing classical mechanical interactions. So in order to set up this problem, we have to do a bit of preliminary work and see where we were. So I will do a bit of recap before we jump into this problem. So since we are going to look at the classical system, one thing to keep in mind is that the microscopic state in classical mechanics, or a microstate in classical mechanics, is fully qualified by giving the point in phase space, right? So if we write down R1, R2, Rn, P1, P2, Pn, where if you're looking in 3D space, then this R is a vector, and in fact you have R1 till R3n. This fully characterizes the microstate of the system. Okay, and I'm going to write it down in a shortcut as R to the power n, P to the power n. So notice this difference between the subscript and the superscript. So the R to the power n is R1, R2, R3, Rn. Okay, all of these things collectively. And this fully qualifies our microstate. And what is it that we want to calculate in StatMech? As usual, we want to calculate some partition function. Let's start with a canonical partition function. It could have been grand canonical also, but then this n itself will fluctuate. So let's say our n is fixed. So we start with a canonical partition function, a q of beta nv or q of nvt, whichever way you want to call it. This will be given by going to each microstate and doing e to the power minus eta b, e to the power minus beta e nu. The question now is, what is e nu, right? So for a generic classical system, e nu comes from the kinetic energy of the system plus the potential energy of the system. Now, most fluids, most conservative Newtonian systems tend to be such that this kinetic energy always depends on the momentum only, and the potential energy always depends on the position only. Okay, and together we call them as the Hamiltonian of the system, H, which is a function of Rn and Pn. So another way of calling this is that H is separable. The Hamiltonian H is separable into kinetic energy, Ke, plus potential energy, Pe. And I called kinetic energy as K and potential energy as U. So furthermore, we know what is the kinetic energy. It is P square over 2m, right? So this H can be written as going to every particle I is equal to 1 to n. And again, this is going to be a vector Pi square by 2m plus U of Rn. It's this U of Rn which really sets interacting systems apart from non-interacting systems. If we had an ideal gas where there is no interaction, then U of Rn would be equal to 0, right? There is no potential energy. In general, however, there will be a U interaction, and that's what makes life complicated. In general, U of Rn is not equal to 0, and that's what makes life quite complicated. And so how do we deal with such problems? So we have to introduce a bit of formalism. We will think about, for a general problem, so we are going to think about the general problem, okay? We will think about the probability of a state, of a microstate, Rn, Pn. What is the probability that you find a system in this vicinity in a classical system will be given by f of Rn Pn is equal to e to the power exp of minus beta h of Rn Pn divided by the partition function. And what is that? That is the integral of drn dpn exp of minus beta h of Rn Pn. Okay, this should be hopefully obvious to everyone. We haven't said anything profound yet. We are just saying probability is equal to e to the power minus beta times energy divided by the partition function. That's how we did things in the canonical partition function in the canonical ensemble. And we have just written it down. And instead of E nu, so we would have written that P nu is equal to e to the power minus beta E nu divided by Q, right? That is the probability in a canonical ensemble. That is the only thing that is stated over here in a slightly different, by writing down what is E nu for a classical system. When we write down this E nu, this is very nice because that can deal with anything, right? That can deal with quantum harmonic oscillators. We spent so much time thinking about quantum harmonic oscillators. Now I'm not talking about quantum harmonic oscillators. I'm coming down to classical mechanics. Okay, now let's look at equation 1 and try to use the fact that this Hamiltonian is separable, that the Hamiltonian can be written as kinetic energy which depends on only momentum and potential energy that depends only on position. Since this is true, since H Rn Pn is equal to K as a function of momentum plus potential energy as a function of Rn, we can write down our probability distribution function f Rn Pn as e to the power minus beta K of Pn e to the power minus beta U of Rn, and their separate partition functions, right? There will be a dPn e to the power minus beta K of Pn, and there will be a drn e to the power minus beta U of Rn. Is that fair? Does everyone agree with it?
Professor, was that like, is it the P of Rn and Pn?
Go ahead. I could not understand what you said.
in the left side of the equation, what is that? P of R and P N?
F of R and Pn.
F of, yeah, okay.
Let me write it down again. So this is the probability F of finding the system at a position Rn and Pn in phase space. So the thing is, these two integrals can be split, and we are going to give them names. We are going to call this one as phi of Pn, and soon we are going to forget about phi of Pn. We are going to completely ignore it. We will focus our entire attention on this second term, which we are going to call capital P of Rn. This is the probability of finding the position, of finding the system with a special value of the atomic of all different coordinates. So remember, this Rn itself is R1, R2, Rn, where every R1 itself can have three components, R11, R12, R13, similarly Rn1, Rn2, Rn3. So it's a 3n numbers if you are looking at 3D space, right? So that's the probability we are talking about. So as I mentioned, we are going to ignore this phi of Pn mostly for a lot of time. I think for the next few classes, we are going to ignore it, but just let's spend a bit of time talking about it before we say bye-bye to it. So phi of Pn is e to the power minus beta k of Pn by integral dPn e to the power minus beta k of Pn. Okay, so let's call this as equation 2. And so now you need to keep in mind that k of Pn itself is separable. K of Pn itself is given by I is equal to 1 to n pi square by 2m. It's as if every particle's kinetic energy is unaware of other particles' kinetic energy. You can just add them together. What does that mean? That means that just like here, this probability was separated into a probability coming from momentum and a probability coming from position. This probability of the full momentum itself can be separated as a product of probabilities coming due to the momentum of different particles, right? Where this phi of pi is equal to e to the power minus beta pi square by 2m integral dpi e to the power minus beta pi square by 2m. So I didn't do anything magical here, just like I took the integral in this equation in the bottom and separated it out, said that, well, this Hamiltonian H is a sum of kinetic energy which depends on momentum and potential energy which depends on position. So instead of doing this very high dimensional integral, I can split it as a product of two slightly lower dimensional integrals. And that's what I'm doing here. So this thing in the denominator will be, what is it really? It is dp1, dp2 till dpn e to the power minus beta kinetic energy, minus beta p1 square by 2m, e to the power minus beta p2 square by 2m, so on and so forth, right? And then you notice that this can also be separated into just integral over dp1 of e to the power minus beta p1 square by 2m, just integral over dp2 of e to the power minus beta p square by 2m, and they are all the same integrals. It's just the variable that is different, name of the variable that is different. Otherwise, they are all the same. So it's a product of n single integrals. And we can how should I go next? What do I want to do next? So we can calculate it, right? Because the momentum can go from minus infinity to plus infinity. So it's just a Gaussian integral. You can go and calculate it. It's not hard. So once you do that, what you get is, let's work through the calculation. So for example, the average value of the momentum average value of the speed, the average value of the momentum will be 0, right? Because you can have, it's an average. If you didn't not have the absolute value over here, then the average value of the momentum would be 0, because this is an even function, and positive momentum and negative momentum are possible with the same probability, so it averages out to 0. But if you're talking about the average speed, you can calculate that by doing integral dp. And now I have removed the subscript pi because this could be for any particle, particle 1, particle 2, particle 3, e to the power minus beta p square by 2m. And in the denominator, you don't have this modulus p, you just have dp e to the power minus beta p square by 2m. And notice the key thing here is that there is no position. The position does not play a role. There is no Rn here. The average value of the momentum can be calculated completely separate from the average value of the position. That's our assumption over here. So you can write this down in spherical coordinates, and this becomes 4 pi 0 to infinity dp p cube e to the power minus beta p square by 2m. And in the denominator, you will have 3 independent components. It will be minus infinity to infinity dp e to the power minus beta p square by 2m whole cube. So it's a bit of an ugly integral. It's not too bad, but the key thing to keep in mind is once you calculate it, you get something that looks like 8 ktm by pi to the power 1 by 2. So you get this square root of temperature relation, which should not surprise you. That is, if you didn't do this integral, you should still have been able to expect that, because you know, as per equipartition, with many of you proudly used in the first problem on homework 3, 1 by 2 mv square on an average is proportional to kt, right? That's what you are rediscovering here by doing this thing, and you are getting the proportionality constant. Similarly, so one point that I wanted to make here is that the average value of the momentum itself is 0. We did not do that, but if this confuses you, work through it and see why it is 0. We don't have to do anything, because momentum can take plus value, can take minus value, and the probability over here is an even function, so we don't have to do anything. Okay, so yeah.
Real quick, why are your bounds for the numerator 0 to infinity instead of negative infinity to infinity?
Oh, I just knock a 2 out.
But if you're doing the spherical coordinates, wouldn't it then be 4 pi times 2? So it should be 8 pi?
It's possible. Let me see one thing. So
Okay.
it could be 8 pi. It could be 8 pi. So you're going to check and tell me, Emma, okay?
Okay.
Okay, right. But the key physics here is it will be square root of temperature, okay? And similarly, the average value of momentum square you can show will be 3 mkt, which is equipartition, exactly. So we are about to get rid of this momentum business, and I just want to make one point here is that the partition function that we had can be written as something that comes from momentum, something that comes from position, something that comes from momentum of all n particle system, all n particles, something that comes from position of all n particles. And if we want to be careful about indistinguishability, we are going to divide it by 1 by n factorial. Why are we going to divide by n factorial? Because we are interested in classical fluids. In classical fluids, so like Nathan mentioned early on, we are not trying to model the protein, but rather we are trying to model the environment of the protein, the solvent in which it is moving around. We are not trying to model. I mean, I think that's the best example I can give you. It's think of the solvent. So in the solvent atoms or in the fluid, the atoms are indistinguishable. That's why we divide by n factorial.
So with the indistinguishable
Uh-huh.
system, like what are the microstates for that? Because
So
like is it the same or
you calculate the microstate for one particle at a time. The microstate is calculated for not for Pn Rn. The microstate is calculated for P1 and R1, right? You
I
calculate the
thought the
microstate.
microstate was like the every single position and every momentum was one microstate.
Yes, but that's why we are using the indistinguishability argument, which works for n factorial. And this is why you can also see that the low density thing is important. If you didn't have low density, you won't be able to do this, right? If you have low density, all particles can kind of hang out wherever you want. And we will work through this. We will be calculating the microstate, so it will become clear. Okay? We won't be
Can I ask quick?
no, no,
Can I ask
stop.
a quick question?
No, wait, I'm finishing to Nathan. So don't jump in. Okay. So
Yeah, it's related, kind of.
no, hold on.
Oh, sure. Okay.
So our idea is going to be to calculate partition function for P1 R1, multiply it to the power n as if things are existing independent of each other, and then divide by n factorial. This will work in certain conditions. This will work in the low density limit. Now you might say, how will this ever have any interactions at all? Why should this just not be like the ideal gas all the time? You will see how that actually falls out when we work through it. And for what's going to follow in 2 minutes, we will ignore the momentum. We will basically focus on microstates only in the coordinate space. Okay. What were you saying, Jingchen? Sorry.
Okay.
Yeah. So quick question regarding on the microstates of the
Mhm.
system. Say, are the microstates of the classical indistinguishable particles the
Mhm.
same as the microstates of bosons?
Correct.
Yeah, I'm a little bit confused about that statement. Can you?
It is a perplexing statement because it is true. The only contradiction that happens in this limit of high density, most classical systems are not extremely dense. So for quantum fluids, that's really true. But if you're thinking about classical fluids, you have to think of the Bose-Einstein in the limit of large n and using Stirling's approximation. So the reason why, so Nathan and Jingchen both ask a very good question. So what is the microstate? And if you really think about it, this n factorial, so first of all, let me write down here some function p of momentum and some function r of position. So this n factorial correction comes at a later stage, right? It doesn't really correct for the microstate itself. It comes much later. If you really want to write down the microstate exactly, you have to deal with Bose-Einstein and assume that particles can take as many states as you wish. But then you also have to take into account that classical system means that the separation in the levels of the Bose-Einstein system has gone to zero and you have a continuous spectrum, right? So that is that limit also that you need to consider. Okay?
Well, so could the microstate for the distinguishable system, the microstate was like the list of positions and velocities? For the indistinguishable system, could it just be like an unordered kind of set
Yeah,
of
that's correct.
positions, so you can
Yeah,
have
that's
them in
correct.
any
That's
order
correct.
you want?
That's correct. And we are just you. It's great that you're all asking the question. Just give me 2 minutes. We are going to talk exactly about things like that. Okay. So it's wonderful. I mean, most professors, especially in Zoom, protest that my students are just in a black screen and no one asks me a question. So it's wonderful that you're asking me. Just give me 2 minutes because we are going to talk exactly about this thing. Okay. Great. So the point that I want to make here is this part can be calculated explicitly. We just wrote it down and I showed you some of the examples, but it comes out to be, so 1 by n factorial is our ad hoc correction, which you saw in your problem 3b. You should be careful in using. But if you are in low density limit, it's okay to use it. That's the point here. multiplied by something which I am going to call de Broglie wavelength to the power 3n multiplied by drn exp of minus beta u rn. And this de Broglie wavelength is lambda t equal to h by square root of 2 pi mkt. Okay, so this equation, I lost my numbering, equation number 3 is the partition function for a classical fluid in low density limit. If it was not low density, then n factorial approximation would not be correct. And it's a classical fluid, so the Hamiltonian is separable into kinetic energy plus potential energy. And what we are really going to deal with now is to focus on this second part of the partition function and really calculate the probability of observing the system in a given microstate. So the questions that you're all getting excited about, especially
Professor, that 1 by lambda t, that is to the power 3n, or
to the power 3n.
3n number of lambda t?
To the power 3n.
Both.
Lambda t multiplied by lambda t multiplied by lambda t 3n times, okay? Lambda t to the power. The point is that it's something that can be integrated out and it exists. We don't worry about it. Our main hero in the remaining part of the next few classes is something which we call the distribution function, which is exactly what I mean, what you were all, Jingchen and Nathan were asking about, is the probability of a certain microstate. And here we will carefully deal with distinguishability and indistinguishability. So how do we define such a distribution function? So a distribution function is defined by the probability of finding a certain particle at R1 and a certain particle at R2. Notice I am not using superscript, so be very careful. Okay, we'll proceed slowly, and I want to emphasize that I'm not using superscript here. I am talking about joint probability distribution for finding particle 1. Okay, so in our fluid, let's say it's water, it's lots of water moving around. We go and tag our water with a deuterium or something like this. And we tag another water with something else. So we know, and by particle, it could be a molecule. I'm just using the word particle, but we are not going to care about the internal structure of the water. So the joint probability distribution for finding particle 1, so the name is important. We are not assuming indistinguishable right now. We are saying it's distinguishable. Particle 1 at position R1 and particle 2 at position R2. Okay, and we are talking about a 2-particle probability distribution. So it's kind of obvious from the fact that you have in the brackets, you have R1 and R2, but just to be super clear, we are going to put it a 2 in the superscript over here. So this is the joint probability distribution for finding specific particle 1 and specific particle 2 at these 2 positions. How do we get this from, and here actually let's go back, and we had names for it, right? So why are we using, we had called it P of Rn, and we had called this phi of Pn, right? So P of Rn is this thing. How do we get this probability from P of Rn? Any idea? What should we do? We should integrate out R3, R4, R5, R6, everything, right? So dr3, dr4, drn, I integrate out all of them. And then what I am left with is the joint probability distribution for finding specific particle 1 at position R1 and specific particle 2 at position R2. This is fine. And look, and this is exactly what I meant when I told Nathan, just to be patient for just a bit. Here we can't just divide by n factorial. It's a bit complicated. But in reality, when you have a box full of, when n is a Avogadro number of atoms, and you have a box, let's say you have a box and you had some solvent over here and you had put in some dye in this, let's say, right? And your dye started in this corner. And as time progresses, the dye diffuses and goes around here and there. And you want to calculate what is the probability of finding two dye atoms at two specific spot. You don't care which dye atom, right? You don't care about the identity. Or even if you ignore the dye, just the box of waters. Let's say you started a system where you had half water in here and then you shake it up and you let everything mix together. And now you want to calculate what is the probability of finding two water molecules, any two water molecules at a spot 1 and a spot 2. How do we do this? So what I mean to say here is, for a system with large n number of particles, we often do not care about the identity of which particles are we thinking about. Identity of the particles. So we are willing to get rid of this specific approximation. We want to come up with a non-specific probability, which tells me what is the probability of finding one particle, any one particle at R1 and any other one particle at R2. Remember, you can't find the same particle at R1 and R2, right? That will be like a sci-fi movie. You can't do that. So the probability of so we want to write down the joint distribution function for finding any particle at R1 and any other. Clearly it can't be any, right? It has to be any other. If you have tagged one particle, it has to be one of the others. So this is any of the n particles you have, and this one is going to be any of the n minus 1 particles you have. Any other particle at R2. This thing, so this P2 of R1, R2 is called a distribution function. This thing that we are going to introduce next is called a reduced distribution function. And this is what we end up caring for more, because most of the time we don't care for the specific identity of the particles we are looking at. We are looking at the reduced distribution function. This has a name, rho. The symbol rho is used for it. And again, rho will be a function of R1 and a function of R2. And we are going to put the superscript 2 over here to specify it's for a two-particle distribution function. And now here is a question that I want you to think about. What is the connection between the reduced distribution function and the true distribution function? Is this true, or what do I need to add here? Any idea? Where is Nathan? Since he was bombarding me with questions, now I'm going to ask Nathan questions. Help me, Nathan.
I don't think you can add anything there.
I think you can.
Oh,
You might not like what I do, but it's one way of doing it. So what I'm going to do here, it's not obvious. I'm going to multiply it by n and n minus 1. I'm going to say this cared for a specific particle, but now that specific particle could have come from any of the n choices. That leaves this other particle, which can now come from any of n minus 1 choices. So one thing to be noticed is that this rho 2 is not normalized anymore, right? It's not a probability density. You can't just multiply by n and something order n square and say it's going to be probability density. So it's a function. It's not exactly probability density. So that's our reduced distribution function. And this is what I meant when you were asking me about microstates. This is our way of dealing with it. Okay?
I have a
Okay,
quick question. Oh, I'm sorry.
Yeah, who had a question?
When we multiplied by n into n minus 1,
Uh-huh.
I was thinking, shouldn't we be multiplying with nc2, which would be n into n minus 1 divided by 2 factorial?
No, because the the order matters. It's a good point. So, okay, you tell me, when would you multiply by NC2 or when would you multiply by NP2? Here, what did we multiply by?
But why would the order matter if, so the order matters if we're choosing, so the order matters in terms of choosing which one we would label as particle 1 and which one we would label as particle 2.
Yeah, yeah.
But I don't quite understand why that should matter when you have.
Because this location of R1 and R2 has been fixed. We are not permuting them. So let's make it one step simpler. This row 2 notation, let's go one step even simpler and let's talk about P1, okay? The probability of finding a specific particle at a location R1, right? We could have written P1 of R1 is equal to integral dr2, dr3, P of Rn, correct? And now I want to calculate the probability, I want to introduce a reduced distribution function which tells me the which is related to the probability of finding any particle at a location R1. That I will define as n multiplied by P1 to the power R1, n multiplied by P1 of R1, okay? So if this confuses you, why not to divide by 2 factorial? I think to be really honest, it doesn't matter because this rho 2 is not going to be a probability density anyway, right? So you could have divided by 2 factorial. It won't change anything. It's something proportional to that. The thing that it captures is the order n square dependence. Whether you divide by 2, you could have defined that way, but we are not talking about probabilities anyway. We are talking about something that is proportional to a probability. And this really is the starting point. If we were talking about the probability of finding a specific particle at R1, and we define this rho 1 R1, which is n times this. So the question now is, what is rho 1 R1? It looks kind of abstract and we don't even know it's a probability, but this rho 1 R1 has a physical significance. Does anyone have a hint or a guess as to what it might turn out to be?
Number density?
It is the density, but not always. It is the density for a uniform isotropic fluid. If you didn't have an isotropic fluid, and then it won't be the density. But for a uniform, and let's see how that happens. And then we will go back to our rho 2, and then we will go further. We will go to not just 2 particle reduced distribution functions, but k particle reduced distribution functions.
Quick confirmation.
Mhm.
So here, are we still talking about the indistinguishable or distinguishable particles?
We started by writing down things for distinguishable particles. And then we are building in our indistinguishability. We are saying we don't care which particle it is.
So you're saying that starting with the first equation on this page, you are discussing the indistinguishable classical particles.
Yeah.
Okay. Yeah.
Because
Then I think the factor of 2 can make sense. From
it can, but what I'm
discussion.
saying is it doesn't matter. It doesn't matter.
What I interpret is that if you are saying that the microstates of the indistinguishable classical particles are the same as the bosonic particles, then we can definitely firstly come up with a CN2, R1, R2, and then plus P2 of R2, R1.
Yeah,
And
look. You're all slightly overthinking it. What I'm saying is I'm defining it this way. Consider this as a definition, okay? Think
okay,
of it as a definition. My reduced distribution function is proportional to the probability, whether you add a 2 or not in the denominator. That has no end dependence. So I don't care about it. This is my definition of the reduced distribution function, okay?
okay,
That's my, it's that's my, my bazooka. It's a definition, okay?
okay.
And now
Yeah,
let's see what it comes out to be for a uniform isotropic fluid. It's almost like exchange correlation in quantum mechanics. What is exchange correlation? Whatever you can't explain is exchange correlation. You just define it that way, if you know what I mean. So for a for a uniform isotropic fluid, we can integrate ρ1 of R1 dR1 is equal to n P1 R1 dR1. This is a probability. It's going to be normalized. It's going to be equal to 1. So this right-hand side is going to be n. And it's a uniform isotropic fluid. So this thing can go outside the integral. dR1 ρ1, because it's uniform. So it doesn't matter which R1 you think about, right? It does not depend on R1. Or ρ1 multiplied by volume is equal to n, or ρ1 is equal to n by v is equal to density of the fluid. So in other words, reduced one particle distribution function is equal to density of the fluid for uniform isotropic fluid. If it was not uniform fluid, then we could not do this, right? We could not just take it out of the integral. We would have to keep it inside the integral and life would be complicated. So ρ1 is equal to ρ. That's good. And by the way, these equations will matter later. So maybe I should number them better. Equation 3. Let's call this one as equation 4, the definition of the distribution function. And let's call this definition of the reduced distribution function as equation 5, the one particle one as equation 6, and this one as equation 7. Okay, so that's great. So we see what is our, and most of the time we are going to worry about uniform isotropic fluids. Okay, so this approximation will stick with us. So what we can do now is to go back and think about our ρ2. How did we define our ρ2? ρ2 of R1, R2 was defined as n minus 1 probability, the probability distribution function, the true distribution function of R1, R2. Now we can generalize it and we can talk about ρk, probability of finding any k particles at R1, R2, Rk, and that will be n minus 1 till n minus, so k plus 1 pk of R1, R2 till Rk, right? Or this is the same as n factorial by n minus k factorial pk of R1, R2, Rk. This is my ρk. At some point, we might think about ρ3, but most of the time, we are going to think about ρ2. So this part of the semester is something which is typically not done in the physics side of StatMech. This is really the StatMech at the heart of chemical physics and chemistry. So that's why I like 687. And many of you who end up taking StatMech in physics end up not learning this business, but it's abstract. So let's proceed carefully and see what we have. So what have we defined so far? we defined a distribution function, right? Which is just the probability of finding specific particles. From that, we introduced something called reduced distribution function, which accounts for the fact that, well, we don't really care which atom is where. We showed that the one particle reduced distribution function for a uniform isotropic fluid is the density of the fluid. And we generalized it to a k particle reduced distribution function. Now we are going to define a third thing, which we will call a decorrelation function. This decorrelation function will have the name G, and we will define it for the general case of k particles. So Gk of R1, R2, Rk. What is this decorrelation function? So in order to understand this decorrelation function, we really have to look at this. We showed that ρ1 for a uniform isotropic fluid is equal to rho. Okay, now let's think about ρ2. What's ρ2 going to be for an ideal gas made of independent molecules? What will be the connection of ρ2 with the density? Will there be any connection? Any ideas? It will be rho squared. Is that clear to everyone?
Isn't there like an extra n-1?
No. There won't be any n-1. How should we prove this? Any ideas?
If the particles are independent, then we can just say that we have particle 1 and particle 2. And then particle 1 is going to give us a density and particle 2 is going to give us a density. So then they should just be multiplied.
That's the right spirit, but can we be more rigorous about this? Do we need to be more rigorous about it?
Well, if they're independent, then isn't P of R1 comma R2 equal to P of R1 times P of R2?
So yeah,
Because they should be.
so you are saying that P2 of R1, R2 is equal to P1 of R1, P2 of R2, right? So, okay,
Yeah.
that's a step. Then how do we go further? How do we show that ρ2 of R1, R2?
But they're also indistinguishable. So that means P2 of R2 equals P1 of R1.
Correct. So this is, let's just call it P of R.
Okay.
Square. Getting there. Almost there, right? It's one of those derivations, like Emma said, you kind of say it's almost true. So what I want to do is, since this is already quite abstract, I'm not going to pile on more on you. And this part, hopefully you will enjoy this. So what I want you to do is to prove this rigorously, and Nathan already helped you, and post on Slack, okay? I want to see this, and I just want to mention one more thing, and then we will stop for the day, is that in general, if this is true, you're going to prove this on Slack, then for a k particle reduced distribution function, you should be able to show that it is simply rho to the power density for an ideal gas. Things are very independent of each other. However, not everything is ideal, right? Things talk to each other. And that's where this decorrelation function comes into account. Decorrelation function says that rho to the power superscript k is not going to be equal to rho to the power k. So the difference between these two things is what we define as the decorrelation function. This is our definition of the decorrelation function, gk of R1, R2, Rk in general. Okay, so this was for ideal gas and this is for in general. And that's our definition of the decorrelation function, is to how much is the k particle reduced distribution function different from simply density raised to the power k. Okay, so this g of k corrects for the dependence of particles. What does it mean? So in an ideal gas, you have a particle over here. It doesn't tell you anything about where the other particles are going to be, except that it cannot be on top of this. But if it's a point particle, you really don't have to worry about it. Ideal gases are point particles, right? So basically, it can be anywhere else. But a real gas is going to have atoms interacting with each other, and every atom has its own field, which says, do not come too close to me, right? You're going to have ionic interactions, all kinds of business happening. You can't come too close to it. It's just hard sphere interaction, even if it's big. So things are stuck at some point. So rho to the power k is not simply rho to the power subscript, the reduced k particle distribution function is not density to the power k. There is going to be some correction, and that correction. So in other words, what we have done here is to define our g of k, the decorrelation function, as how much does the true k particle reduced distribution function differ from simply density to the power k. Okay, so this all looks very abstract. We have k particles coming from n, big number of molecules, this and that. This is where we'll start to simplify our life. We will consider liquid of spherically symmetric molecules. So next class, I'm going to start from here. I will resume all the way from here, but I want to do a bit, since it's abstract, I want you to see the material at least twice. So let me go a bit ahead, and next class, I will start from here. Hopefully one of you will help me with this solution on Slack. We'll go through it together, or I will do it myself. So liquid of spherically symmetric molecules, we are going to think about G2 of R1, R2, which is going to be rho 2 of R1, R2 divided by rho square, right? It's a spherically symmetric molecule. So we are going to care only about the modulus of R1 minus R2, or which is often called R12, which we are just going to call R, right? So for a spherically symmetrical molecule, the decorrelation function, all we care for is G of R. We have omitted the subscript 2 because we are going to care about two particle decorrelation functions, and we have just kept R because we are going to care about spherically symmetric molecules. And this is the real hero of the coming weeks. All of this was a prelude to setting up for G of R. This thing is called radial distribution function. People also often just call it G of R. In fact, in theoretical groups, you will see graduate students running around looking half crazy saying, oh, my G of R is not correct. My G of R is crap. So it's of huge importance in simulations, but also in experiments, because G of R can be directly calculated from X-ray scattering. And we are going to think about G of R. We are going to see how it looks for solid, how it looks for liquid, how it looks for gases, and think about it very, very carefully. But in order to do it, we have to again become familiar with these abstract concepts of distribution functions, reduced distribution functions. So next class, actually what I'm going to do is to walk through this distribution function concept again. And I want someone to prove this on Slack as to why is rho 2 defined this way equal to density square for an ideal gas made of independent molecules. If you prove this on Slack, the first one to prove this gets guaranteed participation points, okay? That's the thing. If you prove that, then you should, hopefully you won't disappear from the meaning of the class, but you can if you want. If you can prove this, the first one to prove this cleanly gets guaranteed participation points. So we will look at that proof next time, and then we will resume by talking about G of R. We will see how it looks. So I will draw the plot actually, and we are going to understand why it is like that. So G of R versus R for crystals looks like delta functions, almost delta functions. For liquids, it tends to look something with broader peaks, and then it goes to 1. For gases, it tends to be even broader. And we are going to understand why all of this happens, what is the understanding behind this. And it's super critical, because when you do neutron scattering or anything, any sort of scattering, you essentially recover the G of R. And why do you care so much about the G of R? Because G of R in the end tells you about U of Rn. What is the potential energy in the system? By doing scattering, you can get G of R. And by inverting this G of R, you can go and tell how do molecules talk to each other? What is the interaction between two molecules? And that, of course, is of great importance. Anyone would agree, right? So this is why all of this is so important. So we are entering this third part of the semester, which is abstract. We will start slowly, so everyone stays on page. Chandler has a whole chapter on this, so we will be closely following it. Please go and read it if anything confuses you. Any questions? And first one to prove this on Slack first one to prove it absolutely correctly gets full participation points. Okay, if no more questions, see you on Thursday. Bye-bye.